So now that we've had a bit of an introduction to parametric functions, it's worth talking about the fact that we can actually take derivatives of parametric functions. But we need a little bit of introduction there. For the purpose of this video, there's going to be three different derivatives that we're looking at. One of them is going to be dx dt, one of them is going to be dy dt, and the last one is going to be one that we're very familiar with, which is dy dx. Right? And the short of it is simply dx dt is just the rate of change of x. So that just tells you how x is changing, right? So if dx dt is positive, it means that the x values are becoming more positive. If dx dt is negative, it means that the x values are getting closer to being negative values. The same is true of dy dt. dy dt is just telling you what is the rate of change of y with respect to t. So if dy dt is positive, y is becoming more positive. If dy dt is negative, it's becoming more negative. And finally, dy dx is exactly what we expect it to be. dy dx is the rate of change of y with respect to x. And we do need a little bit of a formula for that one. Dx dt and dy dt are really simple. You just take the derivative of the x function, or take the derivative of the y function. But to get dy dx, we're going to have to do the rate of change of y with respect to t divided by the rate of change of x with respect to t. And you can sort of mentally imagine that the dt's are canceling out. That doesn't really happen, but it's useful as a way to help us remember what we need to do. So dx dt and dy dt, very easy to compute. Dy dx is actually not that hard. You just have to do the first two things. Okay, I've got a couple examples for us, so we'll get to those now. So this first example, for the following parametric curve, I want us to find dx dt, dy dt, and dy dx, and then find the equation of the tangent line when t equals 1. So first of all, to find dx dt and dy dt, we basically just need to take the derivatives of the x and y functions with respect to t. This should be very easy to do, so pause the video for a second and do that. So dx dt, you should have gotten 6t minus 5. And then for dy dt is 6 minus 3t squared. So great, there they are. Those are dx dt and dy dt. Okay. Next up, we need to find dy dx. And we mentioned previously that if you're going to find dy dx, we need to do dy dt over dx dt. Sorry for my horrible writing today. So let's see, if we actually work this out, we end up using the 6 minus 3t squared that we figured above, divided by the 6t minus 5 that we also figured above, and this thing here is my dy dx function. Okay. The last thing we need is it asks us to find the equation of the tangent line when t equals 1. And I hope you guys remember that for this, we need to have a point, and we also need to have a slope. Right? Well, we know that the slope comes from using dy dx, right? So I can use dy dx, and I can just evaluate this derivative when t equals 1. So if I evaluate this for 1, I'm going to end up with 6 minus 3 over 6 minus 5, so that slope is 3. Now I hope that my first video in the sequence was enough to sort of show you what you're going to need to do to find the point. Right? We want to find the point when time is 1, so we'll plug 1 in. We'll evaluate our x and our y, not piecewise, but parametric functions when x equals 1. So for x, if we evaluate this when x is 1, we'll end up with 3 minus 5, which is negative 2. For our y coordinate, let's see here, we'll have 6 minus 1, which is 5. So that brings us to the idea that the point is negative 2 comma 5. So we've got a point, we've got a slope, so we can use point-slope formula line. Y minus 5 equals 3 times x plus 2. This is the equation of our tangent line to our parametric function at time 1. So I have a second example here that's slightly different. So same thing, I'm asking you for dx dt, dy dt, and dy dx. I'm giving you a parametric curve, and then I'm asking you to find the equation of the tangent line. And there's the one difference here is I'm giving you the point of tangency instead of the time that I want the tangent line. And that on the one hand is easier because we already have the point, but on the other hand may be a little bit harder because we're still going to need to find the slope. So I want you guys to pause the video, do as much of this as you can, and see if you can figure out what you're going to need to do to get through it. Alright, So first up, we find dx dt by taking the derivative of the x component of our parametric function. That's going to be negative sine t. Next up, we find dy dt by taking the derivative of the y component of our parametric function. This gives us 3 cosine t. Next up, we compute what dy dx is by looking at the ratio of dy dt and dx dt. It's going to end up being 3 cosine t over negative sine t. If we wanted to, we could simplify that down to being 3 cotangent t. I'm sort of fine with either one of them. But that gives us our 3 derivatives, our dx dt, our dy dt, and our dy dx. Right. Next up, we need to find the equation of the tangent line. And as I mentioned previously, we know we have the point already. I just need to know what the slope is. So to find the slope, I need to evaluate this function. Right? The issue with that is I need to know what t is, and I was never told what t was. So the question is, and if you haven't figured this out for yourselves, I'm going to ask you to pause the video at this point and sort of figure out this question. How will you figure out what time is? Right? And we covered this in the first video. The idea is, if you have a point, that point should be equal to the x and y components of the parametric function. I should be able to say that 1/2 the x coordinate is equal to cosine t, and I should be able to say that negative 3 root 3 over 2, negative 3 root 3 over 2, should be equal to 3 sine t. So now I can solve both of these functions, solve both these equations rather. So for the first one, where is cosine equal to 1/2? Well, cosine is equal to 1/2, let's see here, when time is pi over 3. It also happens at negative pi over 3. We just sort of need to be aware of all of these because I'm going to need to find the one that works for both of these. For the other equation, I'll need to divide by 3. That'll give me negative root 3 over 2 equals sine t. So now where does this happen? Where do we have a sine value of negative root 3 over 2? Let's see here, a sine value of negative root 3 over 2. That's going to be negative 2 pi over 3 or negative pi over 3. Like those are both places where that happens. So the question is, what time is being used in this problem? Well, the one time that's shared is the negative pi over 3. So that's going to be the time that I'm using for me to find the slope of my tangent line. So now all I need to do is evaluate dy dx. Evaluate dy dx at that time. So that's going to give me negative 3 times the cotangent. Cotangent. Actually, it might just be easier for me to use the simplified version of this one. 3 cosine negative pi over 3 over negative sine of negative pi over 3. And so if I evaluate these things, so let's see here, we know that we're going to have 3 times 1/2 over negative, let's see here, it was actually negative root 3 over 2. So let's see here, that means that my slope, whoops, oh my goodness. There we go, that means that my slope, my dy dx, is 3 over 2 over root 3 over 2, which is 3 over root 3, which simplifies just down to root 3. So, this is my slope. If we remember from back up here, we had x and y coordinates of the point of tangency, and so now all I have to do is actually write this thing. So using our old friend point-slope form, we'll have y plus 3 root 3 over 2. That was, y minus our y component of the point, y coordinate rather. And then we've got x minus 1/2, and this is going to be the equation of our tangent line. How many minutes until the video's done, Enoch? It's 2 seconds until the video's done. Hope that made sense, everybody.